Hello everybody, I'm Marcel Sala from Aimsun Research Projects Department, and in this video I will be showing you our developments in the IMHOTEP project, which aims for seamless door-to-door air journeys. The IMHOTEP project is based in having advanced models for both the airport terminals and the access and egress from them. The later ones are developed at Aimsun, and you can see in the screen part of the model for the London City Airport use case. These models enable an enhanced airport collaborative decision-making to improve reaction when something out of the ordinary happens or is expected to happen. In other words, disruption management. Disruption can be very different in nature, but as examples that we can think are road closures, public transportation strikes, many flights significantly delayed, among many more. All these, if not properly managed, will stress both passengers and the facilities. The end goal of IMHOTEP is to use these models to enable management plans for the air journeys, so they can be as disruption-free as possible. We need to take into account that air journeys are complex, with many different legs. Consider just the journey from the origin to airport terminal, which is highlighted in blue at the slide showing the full journey. The passengers need to choose between many different transportation modes: car, taxi, share car, bus, train, rental car, etc., or a combination of those. The selected mode will in turn impact the time the passenger chooses to start the journey to the airport. Similar level of complexity can happen in the remaining parts of the journey. So there is the need to model passengers or group of passengers like families individually. This is achieved through a passenger activity travel diary, obtained by our partner Nomon in coordination with the information airports have and cell phone data. This enables to perform agent-based modeling of all the passengers. This agent-based modeling is introducing into the Aimsun Next simulation software that we use to provide the models for the IMHOTEP project. For those of you not familiar with Aimsun Next, the video in the previous slide is a recording from an Aimsun Next simulation. These models have the supply side, which is composed by the road network, with roads, streets with various number of lanes and speed limits, intersections with turning lanes, yields, stops or traffic lights with their respective green and red times, the public transportation with their routes, schedules and vehicular capacity. Then there is the demand side. In the IMHOTEP project, demand is split into two parts. One part is origin-destination matrices for background traffic. This means all the traffic that travels through the modeled network but has an origin or destination different than the airport. Then we have the traffic with origin or destination at the airport, which is modeled as individual passengers. This demand is fed into a newly developed agent-based demand module for Aimsun Next that manages the travels to and from the airport. With all this information, the models can run various simulations for the different scenarios and use cases to get simulation traffic data that lets us validate the background traffic. And what is even more important in this context, the travel time of the passengers going to and from the airport. This way it's possible to get the exact time the passengers reach their final destination or the terminal door. This methodology has been applied into two different use cases. These are Palma de Mallorca Airport, which is located at the Mallorca island in Spain, which is a major destination for tourism. So this is a leisure-centered airport, and London City Airport, located at London near the Canary Wharf district, which is a major hub for the finance industry, resulting in London City Airport being used by a great amount of business travelers. This way, IMHOTEP project covers a wide variety of use cases. For the sake of briefness, let's skip some methodological details on how simulations are performed and integrated, and go straight to the typical but not only problems that IMHOTEP needs to manage. In terms of operation, many different situations can lead to similar problematic. For instance, passengers leaving the terminal later than expected, so public transportation services need to run until later. This can be due to delayed incoming flights or problems with baggage handling, just to give a couple of examples. Late arrivals at the terminal leading to potential missed flights can be because of many disruptions in ground access like roadworks, road closures, public transportation strikes, late departures, etc. Accumulation of passengers at the departure terminal can happen because flights are delayed. Some tour operators drop the passengers too early, and other options as well. So, in all those cases, it's possible to take some management actions to improve the situation and mitigate the effects that require coordination between different stakeholders. This is what IMHOTEP project showcases by taking the benefit of how simulation enables the evaluation of different management actions to select the best one overall. These actions are summarized in a series of KPIs that let the manager of the airport select the best strategy to mitigate the disruption. These are shown in a user-friendly interface that lets the final user filter the action they wish. And among many more results, here is shown the mode split accessing the terminal and the travel time distribution between the baseline and the selected management action. Those KPIs are computed based on the simulations that provide the values for each single passenger or vehicle. Here we can see for the Palma de Mallorca case study the process of passengers arriving to the departure terminal on the left side and passengers leaving the arrivals terminal on the right side. This is a visual representation of what is computed in simulations and how individual agents are modeled through the network. Thus, in summary, IMHOTEP project develops a set of tools that enable accurate prediction of future scenarios, letting the selection of the best management strategy. These tools have been developed and validated at Palma de Mallorca and London City airports, but can be transferred to be applied at other airports. Finally, a big thank you to all the IMHOTEP project partners, starting with the coordinator Nomon, continuing with the academic partners, Cranfield University, TU Dresden, Hogeschool van Amsterdam, and the industry partners, ISDEFE, AENA, London City, EMT, and of course ourselves, Aimsun. So, that concludes my presentation of the IMHOTEP project from the Aimsun perspective. If you have any questions or further interest about the project, you can contact us writing to info@aimsun.com.